Today our discussion is going to be on solar cells. This is a topic which is very pertinent and relevant to today's time. The device has existed for over 50 years, but its relevance has increased quite a lot in recent times. Anything related to energy requirements or environment is related to solar cells. So in coming years, we can see much more activities in this area. Now, solar cell basically is a device where we are talking about changing the solar energy into electrical energy directly. There are many other ways of harnessing solar energy, but this is a specific device we are talking about where solar energy is converted into electrical energy. This is also sometimes called as a photovoltaic device or a photovoltaic effect, where photons are creating a voltage inside a device. What I am going to cover in today's lecture is what is a solar cell, what are its basic operating principles. Then I will cover, since we have covered PN junction in great detail, a simple single PN junction solar cell, and that will help in understanding the operating principle. So we will look at PN junction solar cell. After that, we will look at characterization of a solar cell. What are we looking for and how is it related to different material properties? Finally, I will like to list all the losses which limit the efficiency of the solar cell. Look at a simple process which is used for making commercial solar cells. This is basically in silicon, and give a brief update of the field on where we are right now. So at the end of the lecture, I plan to cover all these topics. So first we start with what is a solar cell. So as you can see, the first step in a solar cell is absorption of the solar energy. And we have seen this earlier, that if I have a semiconductor, by virtue of its electronic structure, we can create an electron hole pair as long as the incoming energy that I am bringing is greater than the band gap of the semiconductor. So semiconductor by their material properties are amenable to absorb light, which is greater than their band gap, and create an electron hole pair. Generally this electron hole pair, when it is generated, is bound to each other, but it is possible to free them, and that is the second step, is to create the from absorption of solar energy we create what is called exciton, which are electron and holes are still bound to each other, and the second is from the exciton we create free electron and holes. So basically this can become free from each other and they can move away from each other. In many processes, these two are simultaneous. Almost as soon as they are created, they can be can become free, while in some materials it is not so. So sometimes these are combined processes. Now comes the essential step of the photovoltaic, where electronic devices are important, is we have to have an asymmetry in the structure such that the asymmetry in the structure makes sure that the electrons are collected on one end and the holes on the opposite end, because if there is no discrimination on how the electrons and hole move, they will eventually recombine and you will not get anything. So, there is some asymmetry has to be built in the structure, and that allows the electron and hole movement in opposite directions. Now, there are many ways of creating this asymmetry, and the one which we have been discussing in this course is the p-n junction. P-n junction allows you to build this asymmetry, and that happens because if this particular material that I have made, if I make a p-n junction out of it, I have already shown you earlier that that leads to a built-in field. This is p type. And in equilibrium, such a junction has a built-in field, which means if I have an electron here, by its natural field, it will be going towards this end, which we will call cathode, and a hole here will be going towards the other end, which will be called anode. So, this is the natural discriminating motion of the electron and holes is necessary to get the photovoltaic action. If you did not have that, then electron holes which were free, they will recombine with other electron and holes, and you will not get any generated voltage in the device. Now, because of this action, if I connect this device to the outer load, what is going to happen? I will have electron going to the outer circuit doing the work, and eventually this electron comes back to the anode and recombines with the hole that is created. So, the energy that I had given in creating this electron by the photon is used up in the circuit, and it comes back to the ground state. And then I can keep doing this process. As I bring more energy, I am doing the work in the circuit. So, fourth step is when we connect the solar cell to outer circuit, then the electron goes through the load and returns to anode, where it recombines with the hole. Losing the energy that it got from the photon. I could have told the same story from the hole point of view, the same thing, the hole will go through the circuit and come back and recombine with the electron. But the point is that by using a solar energy, I created a current and a voltage in a circuit which I can use almost like a battery. So, solar cell is like a battery, it is used as a current source, because whatever light I am putting in is generating a current. So, now let us look at the role of the p-n junction in solar cell. Since we know a little bit more about the p-n junction characteristics, it is easier to understand how this is operating. So, we look at a single p-n junction. So, you will recall that in equilibrium, this was the situation. I had a depletion width which we can calculate in terms of doping of the two sides. This is the junction. And if I look at the IV characteristic when I apply a voltage, and I will like to change from IV to current density, because generally we talk about in solar cells current density, the current per centimeter square, to keep the units same for different area solar cells. Then in dark, for an ideal diode, this is the IV characteristics, where the current is given by giving the exponential increase in the forward current and a saturation current in the reverse direction. This we have understood it comes mainly because electrons are diffusing as minority carrier in the p type and holes are diffusing as minority carrier in the n type. Now what has happened? Once I put in photons, I have generated, now because of these photons, I am generating electrons and holes, and the direction they are moving is going to be opposite to the earlier forward current. So you can see that the forward current was coming into the anode, while when I put in the light, the current which is generated is going out of the anode. So this is going to be in the negative j direction using the same convention. So due to the light, I am generating a current which is whatever was its dark current given by this term plus a current due to light photons. Now immediately we can start defining some of the characteristics of a solar cell, which is when you have 0 voltage, that specification is given as the short circuit current, and when you have no current, that is given as the open circuit voltage of a solar cell. So when you are using a solar cell, these are the two parameters which define how much power you can gain from the solar cell. Let us look in more detail what is J photon or J due to the light. J due to the light is basically all the electron hole pairs that I have generated by the light, and it can be generated anywhere. I can generate it in this area, I can generate it in this area. And how does that decide how many are generated? Each photon will be responsible for one electron hole pair for linear processes, and from the surface this is going to go down exponentially, because we know that the way the light gets absorbed in a material is given by, if the intensity here is I naught, given by the absorption coefficient of the material. So electron holes are getting generated more here, and as you go deeper in, less of them are getting generated. But which are being collected? All the ones which are in the field, in the depletion width, they are feeling the field and they are going to be drifted due to the field. So the efficiency for collection for these electron hole pair is going to be maximum in the depletion width. What happens to the electron hole that is generated here? It is not feeling any field, there is no minimal field in this area, so there is no drift force on these free electron and holes. So they generally may recombine or drift or diffuse in either direction, but there is a region which is close to the depletion width, which we define by the diffusion length of the minority carrier on this side. Similarly, there is a region close to the depletion width, which we define by the minority carrier diffusion length on the n side. These electron hole pairs in this region will go towards the depletion width because they are close enough to that, and they will add up to the the current in the light. So the total current that I am getting when I illuminate can be thought of as 3 components. One is all the electron hole pairs which are being generated in the depletion region, and they, by the virtue of the built-in field, will be taken to the 2 sides. But then you have some areas in the p-n junction where you do not have field, and if you have that area, only those electrons which are within the diffusion length of the depletion width will be collected. On the other side, those which are within the diffusion length of the depletion width will be collected on the other side. So the total J photon is going to be due to this, which means anything that is being generated in this part is probably getting lost due to other processes, and I am getting only photocurrent from this area, and so I can calculate that in some cases and generate theoretically what is this procedure. So the J pH is what decides my, is going to be proportional to the at V is equal to 0 is going to be proportional to the source current. So this is, if I calculate my light current at V is equal to 0, which is basically this, is going to be the short circuited current. That is the total current I am generating, which I am able to collect. I may be generating more electron hole pairs which I am not able to collect. So this gives me the picture inside the depletion region, and if I look at this from the, as we will go further, what would I need? I would like to have, in order to collect as many electron holes as I can, I need to have large W. I should make my device such that there is a large built-in region, and I should have less dead NNP region. And by that I mean where you do not have the built-in field, and that is good because if you have that region, that is also adding to the resistance of the device. Okay. So this is the picture of a solar cell in a PN junction, and this is the curve that you would get. So let us now define how would we characterize a solar cell. So solar cell characterization is our next topic. Now it is obvious solar cell is an energy conversion device. So the main characterization for it must come from energy conversion, and that is what it is. It is the efficiency of the solar cell, and it comes from how much power I am collecting from my solar cell divided by how much power I am giving in the solar cell. That decides the efficiency of the solar cell. Now there are other parameters which will decide this efficiency and which will be coming from the JV characteristics. So we've seen in a PN junction device or even in other devices, we will have a JV characteristics which will be given like this. So what is the power out from this solar cell? I can have any value of J corresponding to which I will have a value of V. So at any point that would be the power. But in order to make one definite value, what I like to do is I like to calculate a point at which I have maximum value of J multiplied by maximum value of V. So I maximize the JV product, and that point is the maximum power that I can take. Basically it means that if I put an outer circuit load which will match the J maximum, I will be able to collect the maximum power at this point. So I end up defining my P out in terms of this maximum power that I can get from the solar cell. Now there is one more parameter that one defines with respect to efficiency, and it comes from the fact that if I have an ideal solar cell, then whatever VOC I am generating and whatever JSC I am generating, the maximum in ideal solar cell, it should be a complete rectangle. That means the maximum for an ideal solar cell should be JSC times VOC. But real solar cells look more like this, they are not a rectangle. So another term is defined in that respect, and that is known as fill factor. And it's called, it's basically the ratio of the maximum power point at which I can take the power from the solar cell divided by the ideal maximum point, and it is acronymed as FF. So now with this, my efficiency given eta is nothing but fill factor, and I can now characterize it in terms of these two parameters, short circuit current, open circuit voltage divided by the input power. Just graphically, what does this fill factor signify? This fill factor is saying whatever is the actual loop is, how much is the difference, is the ratio of this area divided by the ideal area, that is the fill factor. So what should be the best value of fill factor? Should go towards 1. So if I have my solar cell characteristics, I can figure out the output maximum power I can draw from that solar cell if I design my circuit correctly. And in order to get this information, I still need to find out what is P in. So let us look at what is the total power that I am bringing into the solar cell. So calculation of P in obviously depends on how much power I am getting from sun on earth, right. So this is a number that I need to know, and this is also a number which is varying from space, time, and how I am collecting the sun power. So there have to be certain standardization for the solar spectrum against which I will characterize my device. And these standard solar spectrums are generated based on the information on actual solar spectrum. And general nature of this spectrum is such that if I plot the sun power in terms of watt per centimeter square per nanometer as a function of lambda, and this ranges almost from 250 to close to 3000 nanometer, and we know the visible range is between 300 to 700 nanometer. Interestingly, the solar spectrum peaks at around 500, 600 nanometer, drops very fast, and then there is a huge tail going towards the larger wavelength. So actually maximum solar spectrum is in the visible range, which is good for us, that is why we are able to see things. Now with respect to this, if I am looking at the solar spectrum and the power that it has in the outer space, it is much more. As the sun is going through the atmosphere of the earth, it is losing some power due to scattering, absorption of the atmosphere. So it depends on where I am. And the first standardization which is given for the spectrum is called air mass 0. And this is the sun energy that you are getting in the space. Then as the sun travels the atmosphere of the earth, its energy is going to be reduced, and it will end up showing some absorption coming from the atmosphere, and that is called air mass 1. This is sun energy on Earth's surface. And then there are other standard spectrums defined as air mass 1.5, 1.8, which depends on if the sun is entering at an angle in the atmosphere, which will have different absorption. But whenever we report the characteristics of a solar cell, we will have to define under what solar spectrum and energy we are reporting it, so that it can be compared with the results of other people. So now that we have some standard information about solar spectrum, there are equipments who simulate this solar spectrum and against which one can measure the efficiency of the sun. Further, it becomes interesting to convert this chart of watts per centimeter per nanometer. What this means is the total power coming per unit area of the surface in each nanometer. It is calculating for each nanometer. So if I need to calculate the total energy coming, I need to multiply this number and add it up. Basically the area under this curve is going to be the total energy coming onto to the point that I am observing. It becomes easier if I change this watt into number of photons, which I can easily do because each photon is h nu or hc by lambda. So I can calculate for each joule how many photons I have, and the convenience comes from the fact because we know that each photon is responsible for one electron hole pair. So then it allows you to think in terms of number of electron hole pairs generated, and that is a exercise that helps in further analysis. So one can change that into number of photons coming per centimeter square per second within a wavelength region, and normally it is taken to be wider, something like 20 nanometer. So I know total number of photons arriving on the at the surface where I am doing the testing. So if I need to now calculate P in, the total energy that I am getting in the sun spectrum, I will integrate over all wavelengths. I will take the flux, this I am defining as the flux at different lambda for photons, and the energy at that lambda for the photons, number of photons times multiplied by energy. If I integrate this, this is my total power in. So what we are characterizing in solar cell is how much power I am collecting from the solar cell and how much total sun power at that point I am able to collect per unit area, and if I take that number, that is the efficiency. Now this is the number that we quote again and again when we describe our solar cell. Keep in mind, whenever we quote this number, we must quote also the standard spectrum we are using for doing this measurement. Now what are these numbers generally like? It depends on which technology or which semiconductor we are going to use, that will decide this, what this number is. Silicon being the most common one, and the one which also we have also discussed extensively. It almost constitutes 90% of the solar cells even today which are fabricated, and its maximum efficiency can be something like 25%, which is if everything is done in a proper way. But commercially what you get is somewhere between 15 to 16. So there is a gap on the theoretical efficiency you can get and what one manufactures, and we will try to see why that gap is there and how one can improve it. So this is where it comes, which basically means the solar cell, silicon solar cell which we buy from the vendor today is converting all the energy that it can cover, only 15% of it you are getting as power. That's not a very efficient device if you think of it, it's only 15% is getting converted. So that is one issue then, is to go to higher efficiency. But then when it comes to generating power, that is probably not the only issue that one worries about. It comes out what cost you are generating that efficiency, that energy, and that is most driving force for technologies is to reduce that cost. So if per unit of electricity generated the cost is too high by silicon, then it is not usable. So that has been the driving force for the solar industry, and we will come to that discussion also. So now you know how to calculate P in, you know how to calculate the P out from the JV characteristics of a solar cell, and the number for a typical silicon commercial cell would be around 15-16%. So where does this rest of the energy goes? Where is the 85% of the energy which we are not able to collect? If I want to just take it as a academic exercise and I want to see what is it that happens to the rest of the 85%. So that's what we are going to look at. So we are going to look at the loss terms. So now we will start from the sun energy that is coming, assuming that is to be 100% as it falls on our solar cell, and then we will look at each loss as we go on. Now the first loss that comes is due to the fact that there is no absorption. If I am using a semiconductor, there is no absorption below the band gap, right. What does that mean? It means that if I have the sun spectrum given in this manner and my band gap of the semiconductor with which I have made the PN junction, and let me take silicon as an example to give you some numbers. So, we will take define these for a silicon, good silicon PN junction, which is ideally defined, which is about 100 micron thick. So, if I take a 100 micron thick well made PN junction, what are the losses that will be there? So, numbers will be defined in that term because it will change depending on the material every time. So, let us look at number from the silicon point of view. So, if this is the band gap for the silicon, it basically means that I am not absorbing any of this P in, that is the first loss. And if I calculate that loss, it is almost 23% of the total loss is coming here. So, that is the first point, is the no absorption below the band gap. So, I have already lost 23% just because my material has a certain band gap. Then the second point is, whatever I am absorbing above Eg, when I am at Eg, I am absorbing exactly the right amount. But if I am absorbing energy above that amount, what happens to that energy? It has to be lost non-radiatively, because it will come down to the EC and then there will be a radiative recombination. So, whatever is the excess photon energy, which is for greater than Eg absorption, it is not used. Why is it not used? Earlier we have discussed that we have conduction band and valence band. If I have exactly Eg, then I take it to the conduction band and I recombine and I get the energy h nu, which is equivalent to the conduction band. But if I absorb more energy and I take the electron to a higher level, this electron will lose its extra energy and come back to the Eg, and this is the loss of the energy. So, even though I am absorbing all along here, any value of the energy which is higher than the Eg is lost in heat. So, I am losing even that part, because electrons quickly come back to the conduction band edge after absorbing the light. And this much part that I am losing of the rest of the spectrum, although I am absorbing, almost comes out to be about 29% in case of silicon. So, you can see that from 1 to 2, because of the absorption and the spectrum the way we have, and we have a single material that we are using, we are almost losing 52% of light. So, you already come down to 52% in absorption only to the efficiency. Now comes the part that I will create electron hole pair and then I will collect them, and how the efficiency will go in that case. So, let us look at the third part where I lose the energy, and this is where I lose the energy because my VOC, the larger it will be, the larger will be the efficiency, and the ideal VOC can go only as high up as band gap or the built-in potential, and it never goes up to that limit. So, it is always little bit less than the band gap. If I could make a device with the maximum Eg, then I will have the best efficiency, but there will always be a lag between VOC. In practical terms, VOC would always be less than Eg when I make the device, and that leads to the in case of silicon almost loss up to 14%, because VOC I cannot increase beyond a certain limit. Although theoretically I should be able to make it as big as the band gap of my material. So, I was at 48%, now I have lost another 14%, that gives me 34%. That is the power I have, but that is not enough. I have the next loss, which is coming basically from the fill factor loss, because this fourth loss is there, because when we made our ideal device, we would have liked it to be this way, but we know the J comes in this manner, and that is because there is a fill factor. So, it is not the JSC VOC that we get less value. So, if I take certain values from that, I will lose additional 5% from here. And this is just from a typical PN junction that I have just calculated assuming ideal value. This is a loss that I am going to see. So, this is my theoretical PN junction efficiency for a silicon device. And it comes to, for a single junction, it be about 29%. But there are still some more loss processes which are there, which ideal PN junction we have not considered. And if I add those loss processes, of which the first one that comes to mind is the series and the shunt resistance. So, when we make a device, because in different ways the interfaces and different layers act, the JV characteristic is not ideal. So, the ideal one with a certain fill factor would have this almost vertical and this almost horizontal, but that does not happen because there is a sheet resistance and a parallel resistance in the device, and as a result one will find the effect of the sheet resistance and the shunt resistance is going to be in the manner that will, for the series resistance it is going to move in this way, and for the shunt resistance it is going to move in this way. So, in addition to that fill factor effect, you have this series and shunt resistance effect which will reduce the fill factor further. So, this is another loss that occurs. So, we can reduce that. Then there is a additional loss which what we call is a collection efficiency loss. What is the collection efficiency loss? I have created by one photon, one electron hole pair, and I am expecting it to be collected at the two ends as long as I am within my depletion zone plus a diffusion length region. But that is not all. What it can also do, the electrons while it is going to the cathode and the hole while it is going to anode can find another electron and recombine, and if it recombines you are not collecting it in the outer circuit, and that is a loss to the current that you can collect. So, this is the loss that I am talking about. To tell you pictorially what can happen is, this is the top surface of the PN junction from where I am collecting the light. This is the bottom contact, and I can have electron hole pair, rather than going in this direction it recombines with the hole. So, this is what I call bulk recombination. And this is where the minority lifetime of the materials becomes important, the quality of the material becomes important, because if it may directly recombine with the hole in the valence band, or there might be traps which are recombination centers, RJ centers, as we talked about RG centers, and they can be the reason for recombination. So, the electron and hole may recombine at this point. So, the quality of the material becomes important in deciding these processes. This bulk recombination can happen here and can also happen here. It is because of the bulk traps or bulk recombination processes, and whatever the rate of recombination, you will lose that much current in the outer circuit. In addition to that, what you have is, you may have recombination at the contacts or at the surfaces. So, you have additionally contact recombination, and again this also can be altered by having a good interface. So, again electron and holes can be lost in this process. Now, overall if I have a good PN junction single device, all these 5 and 6 end up making something like a 4% loss. So, I am talking about a good material, good device structure, this will be about 4% loss. So, a practical device is going to be something like 25%. and that has been achieved. People have made very good devices using highly precise microelectronic processing steps which give efficiencies in the range of 25%. But here is a problem. If you use microelectronics, the way we discussed in an earlier lecture, those are highly precise, expensive fabrication steps, and it makes the cost of photovoltaic very high. So ultimately, the point that we want to get in solar cell is that we want to generate power in low value, and hence the kind of processing steps which are used in solar cell are of low cost, and that adds to the lower value of the efficiency that we get. But then it reduces the cost, so from commercial point of view, it is better to reduce efficiency as well as the cost than to get high efficiency and having a too large a cost. So that's what it is. So although it is possible 25%, if we have good material, good processing, we actually only make 15 to 16%. Okay. So next, I will like to, since I'm talking about processing of silicon solar cell, give you a process flow of making solar cell, which is low cost process flow. So let's talk about silicon. So a typical solar cell which is commercially available looks something like this. It has a P region, then a ohmic contact region for high doping P region, back contact, which is often silver, aluminum, amalgam, or some paste type of thing can also be used. On top, we make the PN junction using a N plus P. So if you recall our discussion, we wanted very large depletion region. So we want to make the doping here is less and doping here very, very high, so that the depletion region is very high here. And then you have an N region, and to that N region one makes contact, and in between part is also covered using a anti-reflection coating. This is the structure of a single cell. Before I go forward, I will like to emphasize that in each cell, if I am making a silicon cell, the kind of open circuit voltage I am generating is only probably less than or in the range of 1 volt, which is very, very small for any practical application. So in order to increase the voltage, when the modules that you see in the market are where lots of cells are connected in the series, and if you want to increase the current, then you can connect them in parallel to increase the current, because the currents are in the range of tens to hundreds of milliampere. So for any actual application, one has to increase this number by putting lots of cells together, and that is a module. So from single cell, we then develop the module, which also has its own technical issues, but that is the main point. So let us think of only a single solar cell and how we will fabricate that. So in this process flow, we first start with the P-type silicon. Now in terms of the cost, this is the part which takes almost 40% of the total cost of silicon manufacturing, and hence there is a lot of effort in trying to reduce cost by changing the processing of this material, or by compromising the quality but still getting good enough efficiencies if you can reduce the cost. So this is almost 40% of the cost. If I take what we call electronic grade silicon, which has of course very high minority lifetime and other things, then that is going to be very, very expensive, and the lifetime of minority carrier is in the range of 20 to 200 microsecond. But that's for electronic grade one. One can make solar cells using that, but the cost of that material is very high. So one can change that to a multicrystalline, it's called multicrystalline silicon. and one takes a hit on the efficiency and also on the minority carrier lifetime, which goes maybe in the range of 1 to 30 microseconds. And then there are other things which are coming up which reduce further the lifetime to some extent, but the cost reduction is much more, so that is still beneficial. So the drive here is basically to reduce the cost, even at the cost of the efficiency. We don't necessarily want 25%, but if I can reduce cost quite a lot, I am still in business to provide power to people. So that is the first step, to reduce cost at p-type silicon itself. The rest of the processing is not that high-end processing or costly processing. In the next process, I will go for cleaning, which is normally done, and then go for the creation of the p-n junction, which one process is to use POCl3. This is used for diffusion of the phosphorus in the silicon. POCl3 is a liquid, and as I mentioned, it can be, one can bubble through nitrogen and oxygen through this to bring it to the surface of the silicon. As it comes to the surface of the silicon, what happens is POCl3 oxidizes, one brings in the oxygen along with it, and it changes into P2O5, which reacts with the silicon and gives phosphorus plus SiO2. And this phosphorus is then doping the original p-type silicon to whatever the process is desired. So by creating this, what we create is, we create a phosphosilicate on the silicon surface through this process, and by annealing it, and then we remove the top removal of silicate glass, which was created in the earlier process. And then the drive-in process for diffusion for phosphorus diffusion. So by this time, what I have done is, I started with the p silicon, created phosphorus doped silicon oxide. The phosphorus, this is p type, not phosphorus. So the phosphorus goes in the p type, creates the junction that I want for n plus. Then I remove the borosilicate that was there and drive in the junction further to its final position. So I have a n plus p junction created through this process. Okay. Then I am going to etch the surface. I am going to deposit silicon nitride or some anti-reflection coating onto this particular surface. There are two ways now to, after anti-reflection coating is deposited, which is to reduce the reflection loss, which we did not consider earlier, but that is, there is going to be some reflection loss also as light comes in. And then we do metal deposition for top contacts. Now here one can use an expensive technique, photolithography technique, but on the other hand, people have shown by using things like screen printing of a silver paste, one can make these contacts. And then the cost is reduced by, rather than if I put silver paste, then there is no way for the light to come in, the light is coming in from this direction, then there is no way for the light to come in. So what it is done is, this metal deposition is interdigitated fingers, where you make sure that there is enough free area for the light to go in, and you are able to collect the electrons which are generated. So this is the top contact structure. Then after this point, I need to still make the back contact. So I go back to a process where I make the back contact. So, I have done N plus emitter P, I have made metal contacts to N plus either photolithography, and I have deposited a anti-reflection coating. On the back side, now I repeat this process, but not for N plus, but to get the P plus. And for that I can use gases like boron bromide or even diborane. Those can be used to oxidize the surface and introduce additional p-type doping. And finally, I will use silver aluminum paste for making the back contact. So, if I see this is not a very, it has avoided, one can avoid using screen printing all the photolithography step and create a solar cell, and that reduces the cost, although we pay for the efficiency by compromising with the materials and the processes themselves. Okay, so finally what I want to talk about is where are we in terms of solar cell technology. I just described to you a single PN junction solar cell, what are the efficiencies that is still the main market presence, single junction solar cell, because the costs are reasonable and people are still trying to put with that cost a higher efficiency, that is the effort that is going on. But there has been tremendous effort in this area in last 40 years. The first generation, as we call it, first generation solar cell are based on this silicon, which we have already seen, or gallium arsenide. Gallium arsenide, by making tandem cell or by making 2 or 3 different kind of absorbers within the cell structure, efficiencies can be increased quite a lot. So, these were the first generation solar cell almost 50 years ago, and they are very well deployed in space area. All the power requirement of the space shuttles are taken from the photovoltaic. So, it is a very established technologies in the space arena, the solar cell. But the problem with those solar cell was the space programs could afford, but for utility the cost is too high, and hence the driving force in development of photovoltaic has been to reduce the cost. So, then came the second generation solar cells, and here it was not to increase the efficiency, it was mainly to reduce the cost. So, the kind of materials which were used were thin films. So, as I mentioned, almost 40% of the cost is in the silicon. So, thin films of amorphous silicon, efficiency goes down to almost 10 to 12%, but the amount of silicon you are using is much less. So, the cost is reduced quite a lot. Amorphous silicon is one material, or it can be hydrogenated also. Other thin films were also there, cadmium telluride, CIGS, copper, indium, gallium, selenide. Individual cell efficiencies are very high for some of these cells, CIGS, but when you put it in the module, it comes down to a lower value. But these have promised much lower cost compared to silicon, and that was the driving force, is to reduce cost of power generated by the solar cell. Then comes a further new region which started almost a decade ago, is the third generation solar cells. And in this, once again the driving force is to reduce cost further, and the example here are dye sensitized cells. Now, as we went from PN junction solar cell to the second generation solar cell, it was basically the processing technology which was very different, But in the third generation, even the mechanisms become very different. It was no more p-n junction dependent, because the type of material and absorption was a very different kind. So dye sensitized cell, organic solar cells, they depend on the discontinuity of the materials to create the photovoltaic action. These consist of third generation solar cell. Now these are much lower efficiencies. Dye sensitized is in the range of 10-12%. Organic solar cell commercially is much smaller, but maximum reported is approximately 8%. So again, efficiency is coming down, but cost is much lower, and that is the driving force for this area. And another fourth generation which people talk about is basically hybrid solar cell, where they are trying to use the benefits of the regular inorganic solar cell with the benefits of the third generation type of solar cell, quantum dots, dye sensitized. We also have quantum dots included. So hybrid solar cell use advantages of both inorganic and organic solar cell, or the third and previous generation solar cell, to get the best efficiency. So in summary, I have covered what a solar cell device, how it works. We looked at a single junction p-n junction solar cell and looked at the loss processes if you have a very good p-n junction solar cell, and what can be the practical efficiency that you can get. And as we saw, almost 50% is lost because we are not able to absorb it. It is lost in the absorption process itself, and hence tandem cell or increasing that absorption enhancement is one of the way of trying to get back some of that efficiency. And then we looked at a processing of silicon solar cell, how at the cost of efficiency we are able to do very simple processing of solar cell and reduce the cost for solar cell. With respect to that, where we are going in terms of the technology and the growth, we have looked at different generations where it's not just the efficiency, it's the cost which is driving the development. With the reduced cost, you want to increase some efficiency to as large as you can.